Hello, this is video 48. I'm going to talk about conservation of momentum. This is a very big topic. We're going to be using this idea for several videos. So the law of conservation of momentum says, in the absence of an external force, the momentum of a system remains unchanged. So in other words, the momentum doesn't change. So this law here, this equation shows that the sum of the initial momenta equal the sum of the final momenta. So when initial equals final, that means it hasn't changed. So then we have it written as m1v1 initial plus m2v2 initial equals m1v1f plus m2v2f. So this is assuming that we have two objects, so the sum of their initial momenta equals the sum of their final momenta. This actually comes from the impulse momentum theorem. We can derive it that way. Your book does a good job doing that, so I'll skip that and we'll just use this theorem. We don't have to worry about deriving it, this law. So the total momentum after an interaction is equal to the total momentum before the interaction. That's what this law is saying. So let's take a look at how to use it. Here's an example with a cannon. So it has a mass of 1,000 kilograms. It launches a cannonball of mass 10 kilograms at a velocity of 100 meters per second. At what speed does the cannon recoil? So first of all, how do we know that we can use the law of conservation of momentum for this problem? So the trick that I have, that I should have written a big note of it, but I forgot to, is we can use conservation of momentum. So use conservation of momentum for all collisions / explosions. So this is one of the easier types of problems that you know when to use the law of conservation of momentum, because it's easy to identify collisions or explosions. Collisions, any two objects coming together. Explosion, any one or two objects coming apart. So if you have that in a problem, use conservation of momentum. The reason that we know we can use conservation of momentum is because there are no external forces during these collisions or explosions. If there are external forces, they're so minuscule that we can ignore them. So let's go ahead and write down the equation. mvi, mv1 initial plus, m1v1 initial plus m2v2 initial equals m1v1 final plus m2v2 final. So this is the law of conservation of momentum. How do we use it? For conservation of momentum problems, I'm a big fan of writing down all the givens. I always do, because it really helps me keep up of all these subscripts here, especially as we start to do collisions in 2 dimensions, where we start having more velocities that we want to keep track of what is what. So I always start by writing down V1 initial, V2 initial, V1 final, and V2 final. And the masses as well, so let's put M1 and M2. And I write that down so that then I can define each one and just keep track of them. So M1, I will call it the cannon. So the cannon has a mass of 1,000 kilograms. And M2 will be the ball, which has a mass of 10 kilograms. So then the trick is really the hardest part in these problems is to define these velocities. Once you define them, plug and chug to find your unknown. So we're only given one speed here, but yet we need 3 velocities in order to find the unknown. So you really have to picture what happens in collisions / explosions. Your initial condition is always what happens right before the collision, immediately before the collision. The final is always what happens immediately after the collision. So it's not like conservation of energy problems where you can choose what's your initial point, what's your final point. Collisions, it's always immediately before and immediately after that collision. So what happens before the collision / explosion? Before the cannon and the ball come apart, well, what happens is that the cannon and the ball are together right before they come apart, and they're just sitting there at rest before the ball is fired. So if you visualize this as the initial condition over here, and then this as the final condition over here, then you realize, okay, well, both of the initial velocities are 0. So this makes our problem so much easier. It's all equal to 0 on the left-hand side. And on the right-hand side, which velocity are we looking for? We're looking for the speed of the cannon. The cannon was m1, so we're looking for v1 final. But we're given the velocity of the ball is 100. So again, the trick to these problems is just to visualize it. Visualize the initial and final points in order to be able to define your variables. So now that we have this, we can solve for our unknown, which is v1f. So v1f, we're going to subtract m2v2f to the other side. Then we're going to divide everything by m1 to get rid of that coefficient. Now we're going to plug in the numbers. We're going to get negative 10 times 100 for v2f over 1000 for m1. That's going to give us negative 1 meters per second. So the recoil velocity is negative. That makes sense because we called anything to the right positive, so it's recoiling to the left, so it's going to be negative. And it makes sense that it recoils much slower than the velocity of the ball. Can you imagine if the cannon recoiled at 100 meters per second? That would be crazy, right? It wouldn't make any sense. That's why the cannon is very massive, so that it can have a much slower recoil velocity. So let's do one more conceptual question to finish out this video. So even though there are numbers here, you really don't need to write down the whole equation. Just kind of do it in your head. You've got two boxes on a frictionless surface. They've been sitting together, but an explosion between them has just pushed them apart. How fast is a 2-kilogram box going? So you have an explosion, so you know you have conservation momentum. You know that they're at rest before the explosion, just like the cannon that we just did. So if the initial momentum is 0, because they're both at rest initially, that means the final momentum has to be 0. That means the momentum of the 1-kilogram box plus the momentum of the 2-kilogram box must equal 0, right? Total momentum, P, equals 0. So the momentum of the first one, like I said, you can do it in your head, is 4 times 1, mass times velocity, but it's negative. So that means the momentum of the 2-kilogram box has to be positive because they have to add up to 0. So it has to be 4. So you can see that the speed is going to have to be 2 meters per second. So that they multiply to 4 and they cancel out the negative 4 of the one going in the opposite direction. So the answer is 2 meters per second. So the point of this is just to be able to really visualize what's happening, that if the initial momentum is 0 because they're both at rest, conservation momentum says the final momentum will be 0 as well. So the two momenta have to cancel each other out. So we've talked about conservation momentum. It applies for all collisions and explosion. Conservation momentum is always conserved. This is usually a question that is asked on a test is is momentum conserved in this collision or in this collision? The answer is always yes.